So what is a servo motor? Before starting with it, let's understand the meaning of the word servo mechanism. Servo mechanism word, it is a combination of two words, servo plus mechanism. Servo is coming from the word servant or slave. Okay, so servo mechanism is defined as servo mechanism is defined as a closed loop control system in which a small input power it controls a larger output power in a strictly proportionate manner. Okay, and in this servo mechanism the controlled variable or the output variable servo mechanism in which we are converting a small input power, it controls a large output power and it is controlling in a strictly proportionate manner. So the controlled variable or the output variable of the servo motor, it is any of the mechanical variable, like it can be position, it can be displacement, or it can be velocity, acceleration, and this output variable or this servo mechanism or the servo systems, they are used in automatic control systems. So the application of these servo systems is in automatic control systems. So servo systems are used in automatic control systems, and these automatic control system, they works on the error signals. Okay, so they are converting these error signals they are used to drive the motors used in servo systems. Now the motors used in the servo systems, they are known as they are called as servo motors. So servo motors are what? They are the motors used in servo systems, and these servo systems are used in automatic control system which works on the error signals. And what does this error signals do? These error signals, they drive the servo motors. So servo motors So servo motors, they drive a final control element, and these motors, they are coupled to the shaft, output shaft, that is the load, through the gear train for power matching. Because what the servo motors, they are basically doing, they are matching, they are, that is they are converting a small power into a large power, okay, in a proportionate manner. So they have to be coupled to the output shaft, that is the load, through the gear train for matching of the power. Now these motors, servo motors, they are used to convert So why we are using these servo motors in control systems? These motors, they convert the electrical signal applied into the angular velocity, that they are converting an electrical signal into a mechanical signal, and that mechanical signal is the angular velocity or the movement of the shaft. That is the electrical signal which is we are applying to the input of the servo motor. It will cause the rotation of the shaft, and the rotation, that is the angular displacement of the shaft, it is the output of the motor. Okay, now what are the requirements which we expect from a good servo motor? Okay, that is, what are the requirements for a servo motor for better or good performance? So let's see the requirements of a good servo motor. The first requirement is that the inertia of the rotor should be as low as possible. Okay, so the first requirement of a good servo motor is that the inertia of the rotor should be very low. Second requirement is that its response, that is the response of the servo motor, should be as fast as possible. Response should be fast, that if we are applying or if we are changing the input signals, then the servo motor quickly responds towards these changes. So for quickly changing error signal, quick response means for quickly changing error signals, it must react with good response. And how we can achieve this fast response? This is achieved by keeping the torque to weight ratio high. So the response of the servo motor should be as fast as possible. It means that if the error signals, they are changing, that is that they are changing their nature, so with the change of the error signal, the servo motor should react very quickly. Okay, and how we can and if this change in the error signal should not affect the performance of the servo motor. Now the third requirement of a good servo motor is it should have linear torque speed characteristics. Fourth is that linear relationship between it should have linear relationship between the electrical control signal and the rotor speed over a wide range. Next, it should be easily reversible. Its operation should be stable. Okay, so let's summarize the requirements of a good servo motor. First is that the inertia of the rotor should be as low as possible. Second is its response should be as fast as possible. Third, it should have linear torque speed characteristics. Fourth is that the servo motor should have linear relationship between electrical control signal and the rotor speed over a wide range. It should be easily reversible and its operation should be stable without any oscillations or overshoot. And last, we have that the motor can withstand the frequency starting operations. Okay, so these were the requirements of a good servo motor. Now let's study the types of servo motors. Now the servo motors, they are classified depending upon the type of the electrical supply which is given to us. So they are classified depending upon the nature of the electric supply which is used for its operation. So according to that, this classification, the servo motors, they are classified into two types, AC and DC servo motors. AC servo motors, they are using the electric supply, that is AC supply, and the DC servo motors, they are using the DC supply. Further, we can classify the DC servo motors into armature controlled and field controlled DC motors. So this is the classification of the servo motors. Servo motors are classified into AC and DC servo motors, and DC servo motors are further classified into armature controlled and field controlled DC servo motors. Now let's study the DC servo motors first. So DC servo motor, it is basically more or less same as the DC motor. Okay, so they are more or less same as normal DC motor. The DC servo motors, they behave like a mechanical device. So DC servo motors, they behaves like a mechanical transducer, and this transducer is converting the DC voltage into a mechanical signal, and this mechanical signal is the angular displacement. Okay, so let's highlighted that it is a mechanical transducer which is converting DC voltage into mechanical signal, and this mechanical signal is the angular displacement. Now all the DC servo motors, they are essentially separately excited type. That is, they are separately excited by the different supply voltages. So they are separately excited type, and why we are using them as separately excited, because it will ensures linear torque speed characteristics. We have studied in the requirements of a good servo motor that a good servo motor should have linear torque speed characteristics. So to have DC servo motor as linear torque should have linear torque speed characteristics, we should use them as separately excited type. Now the control of the DC servo motor, that how we are controlling the DC servo motor. So the control of the DC servo motor, it can be from field side or armature side. And depending upon this control, the DC servo motors, they are classified as either field controlled DC servo motors or armature controlled DC servo motors. These are the two types of the DC servo motor. Now let us study these types of servo motors one by one. First we will start with armature controlled DC servo motor. In this servo motor, the field current, it is kept constant, and the armature current, it is varied. So in this motor, what we are doing, we are keeping the field current as a constant, and we are varying this armature current to control the torque. So the control of the servo motor is on the armature side. That is why it is known as armature controlled DC servo motor. Now let's see the circuit diagram for it. For the armature controlled DC servo motor, we have so this is the circuit diagram for the armature controlled DC servo motor. This is the field side and it is the armature side. Okay, IF is the field current, LF is the field inductance, IF is again the field current, and IA armature current, RA and LA are the resistance and the inductance of the armature side. VA is the armature voltage, TM is the torque, EB is the back EMF, J1 is the moment of inertia, and B is the damper. So this is the circuit diagram. Let's define all these variables. Let RA is the armature resistance. VA is the armature voltage. This armature voltage, it is variable and it is applied to the armature side. Omega M is the angular velocity. EB is the back EMF. J is moment of inertia. IF is the field current. And LF is the field inductance. So we have defined all the variables. Now let us see that the air flux phi it is proportional to field current IF. Okay, so this phi, it will be proportional to IF. Okay, now if we remove this proportionality sign, we have to introduce a constant. So this constant is KF IF. Okay, now the field current IF, if we keep this field current as constant and the armature current IA, it will produce a torque. So if we keep the field current as constant, because in the armature controlled servo motor, the field current is kept as constant. So field current IF is constant and armature current IA it will produce the torque Tm. Why this torque is produced? Because we are applying the armature voltage and VA, and this armature voltage is being varied. So this torque is produced due to application of VA, that is the armature voltage. Now this torque, it in turn, it will produce angular shift in the shaft of the motor. It will, which in turn produces angular shift in the shaft of the motor or in the motor shaft. Now this torque which is produced, that is the Tm, it is proportional to this flux phi. So the produced torque Tm is proportional to the flux phi and the armature current Ia which is producing it. Okay, so the torque Tm, it is proportional to flux phi and armature current, and flux is proportional to the field current. So if we write the equation for it, it will become the torque Tm, it is proportional to phi flux and the armature current Ia. Now remove this proportionality sign, and we also know that flux, it is proportional to If, and we have found out that if we remove this proportionality sign, we can introduce the constant Kf If. So putting the value of phi here, we will have Kf If Ia. Now remove this proportionality sign, we will have Kt Kf If and Ia. Kt is a constant, Kf is a constant, and this field current we have already kept it as constant. So we have these three as a constant in it. So instead of these three constants, we will replace it with a single constant K1, and this is Ia, and K1 is equal to Kt, Kf and If. Okay, so this is the torque, and this torque is proportional to the armature current. So as the speed of the motor shaft increases, a back EMF EB is induced in the armature circuit. Now this back EMF, it is proportional to the speed of the motor shaft, and the direction of the back EMF, it is given by, is opposite to the armature input voltage VA. Okay, so as the speed of the motor it is increasing, a back EMF will be induced, and this back EMF is proportional to the speed of the motor shaft, and direction of the back EMF is opposite to the armature input voltage. So if we write the equation for the back EMF, it will be back EMF. We have said that it is proportional to the angular speed of the shaft, that is omega. So remove this proportionality sign, we will have KB, and omega can be written as d theta by dt. So this is our first equation. Let us give it a number, first equation. Now if we apply Kirchhoff's current law in the armature circuit, we will get, let's first see the diagram. Here we are having the armature circuit. Now if we apply the KCL, then the total voltage drop, that is VA, it will be equals to IARA, okay, this current, plus LA DIA by dt, plus this back EMF. So the voltage drop across the resistance, voltage drop across inductor, plus this back EMF will be equal to VA. So applying the Kirchhoff's current law, that is KCL, in the armature circuit, we get VA, that is the armature voltage, is equal to voltage drop across resistance IARA plus LA DIA by dt, that is voltage drop across the inductor plus the back EMF. Okay, number this equation as second. Now the load torque equation of the motor equation is given by, video is in continuation of the control system component servo motors. So the load torque equation, it is given by J d2 theta by dt square plus, it is the force due to the moment of inertia. Now we have the damper, that is the B, so due to it we will have B d theta by dt, and this whole force, it will be equal to the torque induced in the circuit. So we have Tm, we have already written that Tm, it is equal to K1IA, we have already derived it. So number this equation as 3. Now we have these three equations. Now taking the Laplace transform of the equations, we will get first equation. From first equation we will have the Laplace transform of EB will be EBS equals to, KB is a constant, so it will be written as it is, and the Laplace transform of d theta by dt is S theta S. Okay, number this equation as fourth. Now taking Laplace transform of second equation, we will have VAS equal to IAS RA plus LADIA by dt. So we have SLAIAS plus EBS. Okay, so if we shift this EBS to the left hand side, we will get VAS minus EBS will be equal to, IAS can be taken as common, so it is RA plus SLA IAS. Number this equation as fifth. Now taking Laplace transform of third equation, we will have, this is J d2 theta by dt square, so its Laplace transform will be S square J and theta S plus S B theta S equals to TMS and K1 IAS. So if we take common here, theta s as common, so it will be s square, js square plus bs, theta s equal to Tm number this equation as sixth. So we have these three equations, fourth, fifth and sixth. Now from this fifth equation, if we took the value of IAS, it will be from equation number fifth. We have IAS as VAS minus EBS upon divided by RA plus SLA. So we have VAS minus or we can say that if we put the value of EBS from this fourth equation, so we will have IAS equal to VAS minus EBS is KBS theta S. So minus KBS theta S divided by same as it is the denominator. So this is the value of IAS. Now we have this sixth equation. So putting the value of IAS in this equation, we will get substitute IAS in equation 6. We get here we have JS square plus BS theta S equal to K1 and IAS is so we have put the value of IAS from this equation to this. So let's solve it. We have theta S it will be equals to, we are multiplying here, we are having JS square plus BS, then multiply this here LAS plus RA upon we have K1 plus this KBS equals to VAS. Okay, we have, if we multiply this K1 inside, then it will be K1 KBS theta S, and when we have shifted this to left hand side, because theta S terms will be in left hand side and BS term will be in right hand side. So we have to obtain the ratio of theta S and VAS. So it will be equal to reciprocal of that K1 upon JS square plus BS LAS plus RA plus K1 KBS. Okay, so this is the ratio of theta S and VS. Now to form the transfer function, let's simplify it further. We have theta S by VAS equal to, first put the term here LAS plus RA and then divide this whole term with 1 plus K1 KBS upon JS square plus BS LAS plus RA. Okay, so this we have obtained here the theta s and VAS, the relationship between these two, and this is the transfer function because it is the ratio of the Laplace transform of the output and the input. Okay, output is the angular displacement or angular movement of the shaft, and VAS is the input voltage. So if we draw the block diagram of this servo motor, DC servo motor, armature controlled, then we have the input is VAS. So this is a error detector. Here we are having the input VAS. This is our second input EBS, that is the back EMF. Now this is multiplied with what we have, 1 upon LAS plus RA. Then we have K1 and our output is theta s. Now this output, it is feed back to this error detector and it is multiplied with SKB. So we are getting the equation that EBS, we have obtained it, SKB theta s. We have obtained it here earlier, and what theta s was, it was VAS and multiplied with all these transfer function. If we solve this block diagram, then we are going to get this transfer function only. So we have drawn the block diagram of the armature controlled DC motor. So this was all about the armature controlled DC motor. Now let's study the field controlled DC servo motor. Study the second type of DC servo motor, field controlled DC servo motor. Now in this field controlled DC servo motor, we will keep the armature current as constant and we will vary the field current. Okay. So what we are doing here, we are keeping the variable input voltage VF as we are applying it, and we are keeping the armature current as constant. Earlier in armature controlled, we have kept the armature current, armature voltage as varying, and we are keeping the field current as constant. Here we are doing the reverse of it. So this type of DC servo motor is known as field controlled DC servo motor because the control is on the field side. Now the output of this DC servo motor, field controlled DC servo motor, it is the angular shift in the motor shaft. So here also the output of the motor, it is the angular shift, that is the angular displacement theta. Okay, so let's draw the circuit diagram for this field controlled DC servo motor. We have here we are applying the input, that is the field voltage, and this field voltage is variable. This is the field resistance RF and this is the field inductance LF. Okay, now this current is IF, that is the field current. Now draw the armature side. This is the motor shaft and the current flowing through it is the armature current, and here we are applying the force J1B, or the torque produces J1B, and here Tm. Okay, so this is the armature side of the motor and it is the field side of the motor. So this is the circuit diagram for the field control DC servo motor. Now let's define the variables for it. So let RF is the field resistance, LF is the field inductance, theta is the angular displacement of the motor shaft, Tm is the torque, developed by the motor, B is the coefficient of the viscous friction, viscous friction means the friction due to a liquid. Okay, some oil or some liquid will be used, so the friction provided by it, we have the coefficient of viscous friction as B, and J is the moment of inertia. Okay, IA, that is the armature current, it is kept constant, and because we have kept it constant, the motor shaft is controlled by the field side, that is the input voltage or the field voltage. So motor shaft is controlled by the input voltage VF. Okay, now as we have kept this IA as constant, so as this input voltage VF is applied, a current IA flows through the field circuit, and this current, it will produce a flux in the machine, and this flux, it will produce the torque at the motor shaft. So input voltage, it is applied and it is producing, due to which the current is flowing, and current is producing the flux, flux is further producing the torque, and due to this torque an angular shift takes place in the motor shaft. So all these things are linked. In the input we have applied the voltage. This is our input voltage. Input voltage due to which a current IF is flowing. Current is producing flux. Flux is producing the torque at the motor shaft, and this torque produces the angular shift in the motor shaft. So ultimately what we are getting, in the input we are applying the voltage, and at the output we are getting the angular shift. Okay, so let's derive the equations for it. We have now this torque which is produced at the motor shaft, it will be proportional to the angular shift. So torque is Tm and it is proportional to this field current which is producing it. So if we remove this proportionality sign, we have the constant KFIF. Okay, and what is this constant? It is motor torque constant. We will call it as motor torque constant. Now the equation in the field circuit, if we write the equation for the field circuit, or if we apply the KCL, that is Kirchhoff's current law, in the we apply the KCL and KVL in the field circuit, we will get the field equation as VF equals to RF IF, that is the voltage drop across the resistance, plus the voltage drop across the inductance, DIF by dt. So this is the field equation. Now if we write the torque equation, it will be given by torque equation is J d2 theta by dt square plus B d theta by dt. It is equal to the torque which is induced in the machine. So this is the torque equation. So we have three equations. Tm equals to KFIF, we have the field equation, and we have this torque equation. Now if you take the Laplace transform of these equations, if we take the Laplace transform of this equation number second, we will get SLF plus RF IFS equals to VFS. And if we take the Laplace transform of this torque equation, we will get S square J plus BS theta S equals to TMS. And from the first equation, we have TMS equal to KF IFS. Okay. Now from these two equations, fourth and fifth, if we substitute the values of IFS from here to in this fifth equation, we will get the ratio of theta S and VFS as KF upon SLF plus RF, and we have S squared J plus BS. So what it is the transfer function of the field controlled DC servo motor. Because it is the ratio of the output, that is the angular shift of the motor shaft, and the Laplace transform of the input, that is the field voltage. So it is the transfer function of the field controlled DC servo motor. Now from this transfer function, if we draw the block diagram, then it will be, we have here the input, and input is VFS, the field voltage, and this input voltage, it is multiplied by and here we are getting the output, and output is what? We are getting theta s. Okay, so it is the block diagram representation of field controlled DC servo motor. So we have derived the transfer functions and we have studied both the types of the DC servo motors, armature controlled and field controlled DC servo motors. So we have studied about the two types of DC servo motors, armature controlled and field controlled. Now let's see the differences between these two servo motors. So the first difference is the armature controlled DC servo motors, they give better performance because they are having closed loop. As you see the block diagram which we have represented or which we have drawn for both the armature and field control, if you have noticed that the armature controlled motor was having the control system as closed loop. So we have in a closed loop control system, we have the specifications or we have the criteria to compare the input and the feedback signal, or the feedback signal is the output signal. So we can compare these signals and we can make corrections in it. So armature control DC motor is giving us better performance as compared to the field control DC servo motor because it is having an open loop control system. So armature control, it is giving better performance because it is having closed loop control diagram, and the field control DC servo motor, it is giving us poor performance due to open loop structure. Now the second difference between the two is that the inductance of the armature circuit, it is small or negligible. And hence due to this because this inductance is small, so the torque which is produced, it is also very small, and hence the TA is negligible, and this reduces the order of the system equations also. So if the inductance is small, the torque is negligible, and due to this the order of the system equations is also reduced. So it has a simplified mathematical model because equations are linear, they will be having less order, either 1 or 2, so it is easy to solve the equations of this system. And whereas in this field controlled DC servo motor, the inductance of the field circuit, here we are having the inductance of the armature circuit, and here we are having the inductance of the field circuit. It is not negligible. So this, it offers significant Tm. That is the torque. Now third difference is that the speed of response of this armature controlled DC servo motor to the changing inputs, it is very fast. So speed of response of the motor to changing current is fast. Whereas in field control DC servo motor, the speed of response of the motor to changing current is slow. Okay. Now the last difference between these armature and field control DC servo motor is in this armature control DC servo motor, the damping due to the armature resistance and the friction of the motor due to this damping of the armature resistance and motor friction, an extra damping is produced and this increased damping, it improves the transient response of the system. Whereas in the field controlled DC servo motor, improved damping is not possible. Okay, so these were the differences. Let's summarize them, that what we have written in these differences. First difference is armature control DC motor, it is giving better performance, whereas the field control DC servo motor, it is giving poor performance. Better performance because it is giving us it is having closed loop control system, and here we are having open loop structure. Now the inductance here, it is small and therefore the torque is negligible, so it will reduce the order of the system equations. Whereas in the field control DC servo motor, inductance is not negligible, so it will offer significant torque. The third is that the speed of response of the motor to the changing current, it is fast, whereas in field control the speed of response is slow. And the last difference is that in armature we have increased damping, so it will improve the transient response of the system, whereas in field control the damping is not improved and there is no criteria to improve the damping in it. So these were the differences between the armature controlled DC servo motor and field controlled DC servo motor. So we have completed the DC servo motor. Next we will study about the AC servo motors.